the vast emptiness of space where darkness stretches beyond imagination, there exist objects so powerful, so mysterious, that they challenge our understanding of reality itself. Black holes, these cosmic giants, born from the spectacular deaths of massive stars or lurking in the hearts of galaxies, represent both the ultimate mystery and perhaps the ultimate opportunity. As we gaze into the night sky, considering the twinkling stars and distant galaxies, we often overlook the invisible titans that might one day power civilizations across the cosmos. Throughout human history, we have constantly searched for new energy sources, from the first fires that warmed our ancestors to the nuclear reactions that light our cities today. Our journey has been one of harnessing increasingly powerful forces. But what if the ultimate power source lies not in splitting atoms or capturing sunlight, but in the curved space-time near a spinning vortex of darkness? This is not merely a flight of fancy. The mathematics of general relativity, the observations from our most sophisticated telescopes, and the dreams of theoretical physicists all suggest an intriguing possibility. Could we, someday, harvest the immense energies locked within and around black holes? Consider for a moment the sheer scale of energy we are contemplating. A single stellar mass black hole, formed from the collapse of a star perhaps 20 times more massive than our Sun, contains energy equivalent to billions of years of current human civilization's consumption. The supermassive black holes at the centers of galaxies hold energies almost beyond comprehension, equivalent to the conversion of millions or billions of stars completely into pure energy. Our current energy technologies, impressive as they may seem, are primitive compared to what might be possible. Even nuclear fusion, the process that powers stars and which we still struggle to harness effectively on Earth, pales in comparison to the energy density found in the vicinity of a black hole. Where fusion might convert less than 1% of matter into energy, the theoretical processes near black holes could reach efficiencies approaching 100%. This is not merely an incremental improvement. It represents a fundamental leap in energy production capability. The path to understanding these cosmic power sources begins with Einstein's revolutionary ideas about gravity. When he published his theory of general relativity in 1915, Einstein reimagined gravity not as a force pulling objects together, but as a curvature in the fabric of space-time itself. Massive objects like stars and planets create depressions in this fabric, and other objects follow these contours. A black hole is simply the most extreme version of this principle, a place where space-time curves so severely that it creates a one-way path toward its center. For decades after Einstein's revelation, black holes remained mathematical curiosities. Many physicists, including Einstein himself, doubted they could exist in reality. It wasn't until the 1960s and 70s that the pioneering work of physicists like Stephen Hawking, Roger Penrose, and Kip Thorne began to reveal the true nature of these objects. Their equations showed that not only could black holes exist, but they might be commonplace throughout the universe. The energy contained in a black hole comes primarily from its rotation and its mass. When matter falls into a black hole, its enormous gravitational energy is converted partly into rotational energy and partly into radiation that escapes. This process is astonishingly efficient compared to any energy conversion process we currently employ on Earth. While our most advanced solar panels might convert 20% of sunlight into electricity, and our best nuclear reactors perhaps 40% of nuclear energy into usable power, the processes near black holes could theoretically approach perfect efficiency. As we continue on our journey through this documentary, we will explore these processes in greater detail. We will examine the regions around black holes where space and time behave unlike anywhere else in the universe. We will contemplate the ergosphere, a region outside the event horizon where space itself is dragged along by the black hole's rotation. We will consider how quantum effects near the boundary of black holes might allow for energy extraction, and we will imagine how an advanced civilization might construct the mind-boggling engineering works necessary to capture this energy. Some might question why we should care about such seemingly distant possibilities. After all, the nearest black hole to Earth is thousands of light years away, far beyond our current ability to reach. Yet the study of extreme physics often yields unexpected benefits closer to home. Many of the technologies we rely on today, from GPS satellites to computer chips, depend on understanding relativistic and quantum effects that once seemed purely theoretical. By stretching our minds to contemplate the ultimate power sources in the universe, we expand the boundaries of what might someday be possible. As we drift through this gentle exploration, we will contemplate the nature of these cosmic phenomena, understand the theoretical frameworks that might allow energy extraction, and imagine how future civilizations might construct megastructures capable of capturing this power. We will walk the fine line between established science and measured speculation, acknowledging what we know and what remains tantalizingly beyond our grasp. The story of black hole energy is one of extremes, of temperatures approaching absolute zero and others reaching millions of degrees, of densities so great that matter as we know it ceases to exist, of cosmic engines that power the brightest objects in our universe, and perhaps, someday, of the ultimate sustainable energy source for advanced civilizations. So settle in as we embark on this cosmic journey. Let your mind expand with the possibilities while your body relaxes into contemplative rest. Together, we will explore whether these darkest objects in our universe might someday be the brightest hope for advanced civilizations seeking power among the stars. To understand how we might harvest energy from black holes, we must first comprehend what these mysterious objects truly are. A black hole is not simply an object in space, but rather a region where space and time themselves have been fundamentally altered by an extreme concentration of mass. Let us begin with their birth. Most black holes form when massive stars, those with masses at least 20 times that of our Sun, exhaust their nuclear fuel. Without the outward pressure from nuclear fusion to counterbalance gravity, these stellar giants collapse catastrophically. The core implodes with such violence that protons and electrons are crushed together, forming neutrons in a process that releases an enormous burst of energy, visible across the universe as a supernova explosion. But for the most massive stars, even the resistance of neutrons pressing against each other cannot halt the collapse. Gravity overcomes all known forces, and the core continues to implode. As this collapse proceeds, something remarkable happens. The mass becomes so concentrated that it warps the fabric of space-time to an extreme degree. Imagine a bowling ball resting on a stretched rubber sheet, creating a depression. A black hole is like this, but the depression becomes so deep that it forms a bottomless well. At a certain radius, known as the event horizon, the curvature becomes so severe that nothing, not even light, can escape. This boundary is not a physical surface, but a mathematical threshold, where the escape velocity equals the speed of light. The event horizon represents the point of no return. Cross this boundary, and you are forever cut off from the rest of the universe. No force in nature can prevent your inevitable journey toward the center of the black hole. Even light, the fastest thing in the universe, traveling at 300,000 kilometers per second, cannot escape once it crosses this threshold. This is why we call them black holes. They emit no light of their own, and they trap all light that ventures too close. But what lies beyond the event horizon? At the center of a black hole is what physicists call a singularity. In this region, according to Einstein's theory of general relativity, matter is crushed to infinite density, and space-time is curved to an infinite degree. Of course, infinities in physics usually signal that our theories have broken down. Many scientists believe that a complete theory of quantum gravity will eventually resolve these infinities, but such a theory remains elusive despite decades of work by the brightest minds in physics. The simplest black holes, known as Schwarzschild black holes, are perfectly spherical and non-rotating. Their event horizons can be calculated using a formula derived by Karl Schwarzschild in 1916. For a black hole with the mass of our Sun, the event horizon would be just under 3 kilometers in radius. For one with the mass of Earth, it would be merely 9 millimeters. The relationship is linear. Double the mass, and you double the radius of the event horizon. But most black holes in nature are not of this simple variety. They spin, sometimes at tremendous speeds approaching a significant fraction of the speed of light. These are called Kerr black holes, named after the New Zealand mathematician Roy Kerr, who found the solution to Einstein's equations for rotating black holes in 1963. Rotating black holes are not perfectly spherical, but bulge at their equators due to the centrifugal force of their spin, much like Earth bulges at its equator. The spin of a black hole creates an additional region of interest called the ergosphere. Extending beyond the event horizon, particularly around the equatorial regions, the ergosphere is a region where space-time itself is dragged along by the black hole's rotation. This phenomenon, called frame dragging, occurs to a tiny degree around all rotating bodies, including Earth, but becomes extreme near a rotating black hole. Within the ergosphere, it is impossible to remain stationary with respect to distant stars. All matter and energy are forced to rotate in the same direction as the black hole. This region will become particularly important when we discuss energy extraction mechanisms in later chapters. There are also different categories of black holes based on their mass. Stellar mass black holes, formed from collapsed stars, typically have masses between 5 and several tens of solar masses. The first confirmed black hole, Cygnus X1, discovered in 1964, falls into this category with a mass approximately 15 times that of our Sun. At the opposite extreme are supermassive black holes, with masses millions to billions of times that of our Sun. These giants reside at the centers of most galaxies, including our own Milky Way. The supermassive black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. Yet despite this enormous mass, its event horizon would fit comfortably within the orbit of Mercury. The supermassive black hole at the center of the galaxy, M87, the first ever to be directly imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion suns. Between these extremes lie intermediate mass black holes, with masses hundreds to thousands of times that of our Sun. Evidence for their existence has been more elusive, though astronomers have identified several candidates in recent years. These intermediate black holes might form through the merger of multiple stellar mass black holes or through direct collapse of extremely massive gas clouds in the early universe. There are also hypothetical primordial black holes, which might have formed in the extreme conditions of the early universe, moments after the Big Bang. These could theoretically have any mass, from microscopic to massive, and if they exist in significant numbers, might constitute some of the mysterious dark matter that astronomers believe makes up about 85% of all matter in the universe. What makes black holes so fascinating is that they represent a boundary between our current understanding of physics and the unknown. The general theory of relativity, which describes gravity and the large-scale structure of the universe, predicts that within a black hole, our conventional notions of space and time break down completely. Meanwhile, quantum mechanics, which governs the behavior of matter at the smallest scales, suggests that information cannot be truly destroyed, seemingly contradicting what happens when matter falls into a black hole. This tension between our two most successful physical theories has spawned decades of theoretical work and continues to drive research today. From an energy perspective, black holes are remarkable objects. The gravitational potential energy of matter falling into a black hole is enormous. As material spirals inward, it can be heated to millions of degrees, creating some of the brightest objects in the universe. The conversion of gravitational potential energy to heat, light, and other forms of radiation in the vicinity of a black hole is far more efficient than any energy generation mechanism we currently employ on Earth. Consider this. If we could convert matter to energy with perfect efficiency, as described by Einstein's famous equation E equals mc squared, 1 kilogram of matter would yield about 9 times 10 to the 16th joules of energy. This is roughly equivalent to the energy produced by all human civilization in an entire year. Near a black hole, processes exist that can approach this theoretical maximum efficiency, far exceeding the approximately 1% efficiency of nuclear fusion occurring in the core of our Sun. The extreme physics near black holes creates other interesting phenomena as well. Magnetic fields threading through the material falling into a black hole can become twisted and amplified, launching jets of particles moving at nearly the speed of light. These jets can extend for millions of light years, influencing the evolution of entire galaxies. The radiation from material just outside the event horizon can be so intense that it pushes away gas from the surrounding regions, regulating the growth of both the black hole and its host galaxy in a cosmic feedback loop. Despite their names suggesting emptiness and darkness, black holes are actually the most efficient engines of energy transformation in the universe. They convert gravitational potential energy into heat, light, motion, and magnetic energy with unparalleled efficiency. And it is this property, more than any other, that makes them potential energy sources for advanced civilizations. The universe has already built these perfect engines. Theoretically, we would only need to find ways to tap into their output. As we continue our exploration, remember that black holes are not merely destructive entities that consume everything in their path. They are also creative forces that shape galaxies, drive the evolution of cosmic structures, and might one day serve as the ultimate power plants for civilizations far more advanced than our own. The darkness of a black hole might just be the key to illuminating the future of intelligent life in the universe. While the black hole itself may appear as an ultimate abyss, it is the regions surrounding these cosmic phenomena that offer the most promise for energy harvesting. The environment around a black hole is perhaps the most energetic place in our universe, a natural laboratory where matter and energy are transformed in ways that make our most advanced technologies seem primitive by comparison. Let us begin by considering what happens as matter approaches a black hole. In isolation, a black hole would truly be dark, emitting nothing but the faint quantum whisper of Hawking radiation. But black holes rarely exist in perfect isolation. Throughout the cosmos, they attract gas, dust, and even stars that venture too close. As this material approaches the black hole, an elaborate celestial dance begins, one that releases enormous amounts of energy. The most visible manifestation of this energy release is the accretion disk, a flattened band of superheated matter spiraling toward the event horizon. Imagine rivers of gas flowing through space, gradually drawn toward the black hole. As these streams of matter approach, they cannot simply fall straight in. Just as water circling a drain spins faster as it approaches the center, conservation of angular momentum forces this cosmic material into a rapidly rotating disk. The physics of accretion disks is a fascinating blend of gravity, fluid dynamics, magnetism, and relativistic effects. As matter spirals inward through the disk, it experiences tremendous friction. Particles collide with each other at increasing speeds, converting their gravitational potential energy into heat. This process creates temperatures that can reach millions of degrees. At such extreme temperatures, the matter transforms into plasma, a state where electrons are stripped from their atoms, creating a charged, highly conductive fluid that interacts strongly with magnetic fields. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of tens of millions of degrees. To put this in perspective, the center of our Sun is approximately 15 million degrees. The core of a nuclear explosion might momentarily reach temperatures of hundreds of millions of degrees. But the inner accretion disk of an actively feeding black hole maintains these extraordinary temperatures continuously, powered solely by the conversion of gravitational energy into heat. This heat causes the disk to glow intensely, primarily in X-rays and ultraviolet light. In fact, accreting black holes are among the brightest X-ray sources in the universe. The first black hole ever discovered, Cygnus X1, was initially identified precisely because it was such a powerful source of X-rays. These high-energy photons are direct evidence of the enormous amounts of energy being released as matter spirals toward the event horizon. The efficiency of this energy conversion process is remarkable. In conventional energy generation on Earth, efficiency is measured by what percentage of the available energy in a fuel source is converted to usable energy. Coal power plants operate at around 30 to 40% efficiency. Nuclear fission plants achieve similar numbers. Even nuclear fusion, the process powering our sun, converts less than 1% of its mass to energy. But in the extreme environment near a black hole, the conversion of gravitational potential energy to radiation can reach efficiencies of over 20% for a non-rotating black hole, and potentially up to 40% for a rapidly spinning one. This means that for every kilogram of matter falling into a black hole, up to 400 grams of that mass can be converted directly into energy before it crosses the event horizon. According to Einstein's equation E equals mc squared, this represents an almost inconceivable amount of energy, far beyond what any terrestrial power source could achieve from the same amount of matter. The accretion disk is not uniform in structure. Its properties change dramatically with distance from the black hole. The outer regions might be relatively cool, perhaps a few thousand degrees, and consist primarily of atomic gas. Moving inward, the temperature rises rapidly. At around 100,000 degrees, most matter is ionized, forming plasma. At millions of degrees, even heavy elements like iron are stripped of nearly all their electrons. The innermost stable orbit, the closest a particle can circle the black hole without inevitably falling in, marks the inner edge of the accretion disk. Here, the superheated plasma emits intensely in X-rays before taking its final plunge across the event horizon. For a non-rotating black hole, this innermost stable orbit is at 3 times the radius of the event horizon. For maximally rotating black holes, it can be much closer, almost touching the event horizon itself. This difference has profound implications for energy extraction, as we will explore in later chapters. The extreme conditions in accretion disks create fascinating phenomena. Turbulence in the superheated plasma generates and amplifies magnetic fields. These fields become twisted and concentrated as the rotating matter drags them along. Eventually, the magnetic pressure can become so intense that it launches material away from the disk in powerful outflows. The most spectacular of these are relativistic jets, narrow beams of particles accelerated to speeds approaching that of light. These jets are among the most remarkable structures in the universe. They can extend for hundreds of thousands or even millions of light years, far larger than the galaxies that host them. The energy required to create such structures is enormous, equivalent to the complete conversion of millions or billions of solar masses into pure energy over the lifetime of the jet. For comparison, all of human civilization currently uses energy equivalent to converting less than 10,000 tons of matter into energy each year. The mechanism that powers these jets is still not fully understood, but it involves a complex interaction between the black hole's spin, the accretion disk, and magnetic fields. One leading theory, the Blandford-Znajek process, which we will explore in more detail in Chapter 4, suggests that magnetic field lines threading the black hole's ergosphere can extract rotational energy directly from the black hole itself. This would make the jet essentially powered by the black hole's spin, a cosmic version of a hydroelectric dam extracting energy from a rotating reservoir. Intriguingly, not all of the matter that approaches a black hole is destined to cross the event horizon. The intense radiation from the inner accretion disk exerts pressure on infalling material, potentially driving powerful winds that escape the black hole entirely. These winds can be so strong that they regulate the growth of both the black hole and its host galaxy, illustrating how energy around black holes shapes cosmic evolution on the largest scales. The balance between incoming matter, outgoing radiation, and escaping winds creates a self-regulating system. If too much matter tries to fall in at once, the increased radiation drives stronger winds, pushing away the excess. This feedback mechanism prevents black holes from growing at arbitrarily fast rates, and may explain why supermassive black holes and their host galaxies appear to grow in tandem throughout cosmic history. Let us now consider quasars, the most luminous persistent objects in the universe. These are supermassive black holes undergoing extreme accretion, found primarily in the distant early universe. A typical quasar might shine with the light of 1 trillion suns, outshining the entire galaxy in which it resides. Yet all this energy emerges from a region smaller than our solar system, making quasars the most efficient natural energy generators known. The power output of a quasar would be sufficient to meet the energy needs of countless advanced civilizations. A single moderate quasar produces more energy in 1 second than all of human civilization has used throughout its entire history. This represents an almost unimaginable resource for any civilization advanced enough to capture even a small fraction of it. But not all of the energy near a black hole is in the form of electromagnetic radiation. Gravitational potential energy, kinetic energy of rotating matter, and magnetic field energy all exist in abundance. An advanced civilization seeking to harness a black hole's energy would have multiple options to consider, depending on its technological capabilities and specific needs. For instance, the difference in gravitational potential between 2 points near a black hole could be used to generate power, similar to how we use the height difference of water in hydroelectric dams. The extreme version of this would involve dropping matter toward the black hole and capturing the radiation it emits before it crosses the event horizon. Another possibility involves the ergosphere, that region around a rotating black hole where space-time itself is dragged along by the black hole's spin. Within this region, it is theoretically possible to extract rotational energy directly from the black hole through processes we will examine in upcoming chapters. This energy comes not from matter falling in, but from the black hole's own angular momentum, gradually slowing its rotation. There is also significant energy stored in the strong magnetic fields near accreting black holes. These fields become twisted and amplified as they thread through the accretion disk and potentially through the black hole itself. The sudden reconnection of magnetic field lines releases enormous amounts of energy, similar to solar flares, but on a much larger scale. This process helps power the relativistic jets and could potentially be harnessed by sufficiently advanced technology. It is important to note that the energy environment around different types of black holes varies considerably. A stellar mass black hole in a binary system, steadily accreting matter from its companion star, creates a relatively stable energy source that could potentially be utilized for thousands or millions of years. The supermassive black hole at the center of a quasar provides a far larger but potentially more volatile energy supply, with powerful radiation that would create significant engineering challenges for any civilization attempting to harness it. Intermediate mass black holes might offer an attractive compromise. Large enough to provide substantial energy, but not so massive that they dominate their surroundings, these black holes could potentially be used by advanced civilizations as controlled power sources. Their more moderate radiation output would present fewer challenges for materials and shielding, while still offering energy far beyond what conventional stellar or even antimatter power sources could provide. When we imagine harnessing the energy around black holes, we must also consider the extreme nature of space-time in these regions. Close to a black hole, time itself runs differently compared to regions farther away. This gravitational time dilation means that processes near the black hole appear slowed down when viewed from a distance. For energy harvesting, this creates both challenges and opportunities. Energy extraction might need to occur on extremely short timescales in the harvester's reference frame, while appearing much slower to the civilization utilizing the energy. The warped space-time near a black hole also affects the trajectories of particles and light in ways that must be accounted for in any energy collection system. Light does not travel in straight lines, but follows curved paths dictated by the black hole's gravity. Particles might orbit multiple times before either escaping or falling in. These effects would need to be precisely calculated and incorporated into the design of any black hole energy harvesting system. We should also consider the potential for natural energy harvesting that may already be occurring in the universe. Some binary systems containing black holes show evidence of relativistic jets preferentially launched in certain directions or periodic variations in their energy output. These could potentially be explained by the natural equivalent of energy extraction processes that we will discuss in later chapters. Nature may have already implemented some form of the Penrose process or Blandford-Znajek mechanism in these systems. The magnetic fields around accreting black holes deserve special attention. Unlike the gravitational field, which is determined solely by the black hole's mass and spin, magnetic fields depend on the properties of the surrounding matter. The conducting plasma in the accretion disk can sustain and amplify these fields to strengths millions or billions of times greater than those we can create in laboratories on Earth. When magnetic field lines near a black hole reconnect, they can accelerate particles to enormous energies. This process may be responsible for some of the highest energy cosmic rays detected on Earth, particles with energies millions of times greater than those produced in our most powerful particle accelerators. If we could somehow harness this natural particle acceleration, it would represent an energy source far beyond current human capabilities. Computer simulations of accreting black holes reveal complex, dynamic systems where matter, energy, magnetic fields, and warped space-time interact in fascinating ways. These simulations show the formation of turbulent eddies in the accretion disk, the launching of jets, and the generation of powerful outflows. They also reveal quasi-periodic oscillations, regular variations in the system's brightness that may be caused by matter orbiting close to the event horizon or waves propagating through the accretion disk. Such oscillations could potentially be harnessed by advanced civilizations as a way to extract energy rhythmically, similar to how we use the regular oscillations of electromagnetic fields in alternating current electrical systems. The natural frequency of these oscillations depends on the black hole's mass, with smaller black holes producing higher frequency variations that might be more suitable for certain types of energy extraction. The study of black hole accretion and outflows has practical applications even for current human technology. The physics of plasma behavior in strong gravitational and magnetic fields helps us understand similar processes in fusion reactors, albeit on a much smaller scale. The extreme particle acceleration near black holes provides insights into high-energy physics that complement our accelerator experiments. The relativistic jets give us natural laboratories for studying matter under conditions we cannot reproduce on Earth. As we think about the potential for harvesting energy from regions around black holes, we should also consider the cosmic timescales involved. Black holes are incredibly long-lived objects. A stellar mass black hole will persist for unimaginably long periods, far outlasting the stars themselves. The larger supermassive black holes might eventually radiate away their mass through Hawking radiation, but this would take timescales on the order of 10 to the power of 100 years, far longer than the current age of the universe. This permanence makes black holes attractive as long-term energy sources for truly advanced civilizations. While stars burn out and galaxies disperse, black holes remain. In the far future of the universe, when normal stellar energy sources have been exhausted, black holes may represent the last available reservoirs of extractable energy, potentially extending the lifetime of advanced civilizations by many orders of magnitude. The energy around black holes also takes forms beyond what we commonly consider. Gravitational waves, ripples in space-time itself, are produced when objects move in the strong gravitational field near a black hole. When two black holes merge, they release enormous amounts of energy in gravitational waves, briefly outshining all the stars in the observable universe combined, though not in electromagnetic radiation. While we currently have no way to convert gravitational wave energy into useful forms, a sufficiently advanced civilization might develop such technology. Another exotic form of energy exists in the form of frame dragging, the process by which a rotating black hole pulls space-time along with it. This effect creates a kind of gravitational vortex that forces everything within the ergosphere to rotate. The energy contained in this rotating space-time is what makes processes like the Penrose mechanism, which we will discuss in the next chapter, possible. In a sense, the black hole stores rotational energy not just in its own mass, but in the very fabric of space-time surrounding it. The quantum effects near black holes create additional possibilities for energy. Hawking radiation, the thermal emission predicted to occur due to quantum effects near the event horizon, provides a direct way for black holes to lose mass and energy. For stellar mass and larger black holes, this radiation is extremely feeble, with temperatures far below even the cosmic microwave background. But for microscopic black holes, if they exist, Hawking radiation would be intense. A black hole with the mass of a mountain might shine as brightly as a small star through this quantum process alone. The vacuum fluctuations that give rise to Hawking radiation might potentially be harnessed more directly by advanced technology positioned near the event horizon. The extreme gradient in gravitational potential could allow for the extraction of energy from the quantum vacuum itself, effectively mining the exotic physics at this boundary between classical and quantum regimes. There are also theoretical possibilities for energy harvesting that we are only beginning to explore. The holographic principle, a concept from string theory and quantum gravity, suggests that all the information contained in a volume of space can be encoded on its boundary. Applied to black holes, this leads to the idea that the three-dimensional physics inside the event horizon can be completely described by two-dimensional quantum physics on the horizon itself. If this principle is correct, it might open entirely new avenues for understanding and potentially utilizing the energy of black holes. As we contemplate these possibilities, we should remember that our current understanding of physics breaks down at the singularity inside a black hole. A complete theory of quantum gravity might reveal new physics that could further expand the potential for energy extraction. The theoretical tools being developed in fields like string theory, loop quantum gravity, and causal set theory might someday provide insights that transform our understanding of these cosmic objects. We are now ready to delve deeper into specific mechanisms that could allow advanced civilizations to harness the energy around black holes. In the next chapter, we will explore the Penrose process, a theoretical method for extracting rotational energy from a black hole's ergosphere. This fascinating concept, first proposed by mathematician Roger Penrose in 1969, represents one of the most promising approaches for black hole energy harvesting. As we move forward in our exploration, keep in mind that while much of what we discuss remains theoretical, it is firmly grounded in our current understanding of physics. The enormous energies available around black holes are not speculative. They are observed throughout the universe in the form of quasars, active galactic nuclei, and microquasars. What remains speculative is how, or whether, intelligent civilizations might someday tap into these cosmic power sources. The energy environments around black holes represent both the most extreme and the most efficient natural processes in our universe. From the superheated plasma of accretion disks to the relativistic jets that can extend for millions of light years, from the twisted magnetic fields to the warped space-time of the ergosphere, these regions offer unparalleled opportunities for energy harvesting. Understanding these environments is the first step toward imagining how they might someday power civilizations across the cosmos. Having explored the general energy environment around black holes, we now turn our attention to one of the most fascinating theoretical mechanisms for extracting energy directly from these cosmic phenomena. The Penrose process, named after the renowned British mathematical physicist Roger Penrose, who first described it in 1969, represents perhaps the most elegant method for harvesting energy from a spinning black hole. To understand this remarkable process, we must first revisit the unique region known as the ergosphere. As we discussed earlier, a rotating black hole drags the fabric of space-time around it, creating a region outside the event horizon where nothing can remain stationary with respect to distant stars. This region, shaped like an oblate spheroid, flattened at the poles and bulging at the equator, is called the ergosphere, from the Greek word ergon meaning work or energy. The outer boundary of the ergosphere is called the static limit. Beyond this boundary, it is still possible for objects to remain at rest relative to distant observers. But once you cross the static limit and enter the ergosphere, the rotation of spacetime becomes so strong that all matter and energy are forced to rotate in the same direction as the black hole. Importantly, while nothing can escape from within the event horizon, objects within the ergosphere can still escape to the outside universe. This critical distinction is what makes the Penrose process possible. Now, imagine an advanced civilization sending a spacecraft toward the ergosphere of a rotating black hole. This spacecraft carries a payload, perhaps a large mass or container of matter. As the spacecraft approaches the ergosphere, it executes a carefully planned maneuver. Just as it crosses into this region of swirling space-time, it splits into two parts. One part, containing most of the mass, is sent on a trajectory that falls deeper toward the black hole, while a smaller part is configured to escape back to the outside universe. Here is where the magic of the Penrose process occurs. If calculated correctly, the infalling portion can be made to enter what physicists call a negative energy orbit. From our everyday perspective, negative energy seems impossible. But in the strange realm of the ergosphere, where space-time itself is rotating, the total energy of an object as measured by a distant observer can indeed become negative. When this happens, the escaping portion of the spacecraft receives an energy boost greater than the total energy the combined system had when it entered the ergosphere. This excess energy comes directly from the rotational energy of the black hole itself. The black hole pays an energy debt, so to speak, by slowing its rotation ever so slightly. Let us consider this process in more detail using a simplified example. Imagine a particle with energy E entering the ergosphere and splitting into two parts. One part falls into the black hole with negative energy. Let's call this negative E prime, while the other escapes with energy E plus the absolute value of E prime. In this transaction, the black hole loses rotational energy equal to the absolute value of E prime, which is transferred to the escaping particle. This might seem to violate conservation of energy, but it does not. The total energy of the system, including the black hole's rotational energy, remains constant. What the Penrose process accomplishes is a transfer of energy from the black hole's rotation to the escaping particle. The mathematics behind this process are complex, involving the equations of general relativity and careful analysis of particle trajectories in curved space-time. But the underlying principle can be understood intuitively by considering a related phenomenon. Imagine throwing a ball against a moving train in such a way that the ball bounces off and returns to you faster than you threw it. The ball has extracted some of the train's kinetic energy. The Penrose process works on a similar principle, but in the context of rotating space-time rather than moving matter. Theoretically, the Penrose process allows for extremely efficient energy extraction. A single particle following an optimal trajectory can escape with significantly more energy than it entered with. Repeated application of this process could extract substantial amounts of energy from the black hole over time, gradually slowing its rotation. It is important to note that while the Penrose process can extract rotational energy from a black hole, it cannot reduce the black hole's mass. The irreducible mass of the black hole, associated with its event horizon area, remains unchanged. Only the rotational component of its energy can be extracted. For a maximally spinning black hole, this rotational energy can account for approximately 29% of its total mass energy. The efficiency of the Penrose process depends crucially on the black hole's spin. A faster spinning black hole has a larger ergosphere and allows for greater energy amplification. Theoretical calculations suggest that for a maximally rotating black hole, the escaping particle could have up to 20 times the energy of the original particle entering the ergosphere. While we have described the Penrose process using discrete particles or spacecraft, a more practical implementation might involve continuous streams of matter. Imagine a flow of plasma directed into the ergosphere at precisely calculated angles, with a portion falling into the black hole on negative energy orbits, while the remainder escapes with amplified energy. This continuous version of the Penrose process could potentially extract energy at a steady rate. Advanced civilizations might also enhance the basic Penrose process by incorporating electromagnetic fields. Charged particles in the ergosphere experience complex interactions between the gravitational field of the black hole and any magnetic fields present. These interactions can potentially increase the efficiency of energy extraction beyond what is possible with neutral particles alone. One variation of the Penrose process, sometimes called the super-radiant scattering process, involves waves rather than particles. When electromagnetic waves of certain frequencies enter the ergosphere at the right angles, they can be scattered with increased amplitude and energy. The mathematics of this process are closely related to those of the particle version, but the implementation would be quite different. Instead of sending matter into the ergosphere, an advanced civilization might direct carefully tuned beams of radiation, perhaps in the radio or microwave spectrum, and collect the amplified waves that emerge. Another intriguing variation is the magnetic Penrose process, which combines aspects of the basic mechanism with the effects of electromagnetic fields threading the ergosphere. In this scenario, charged particles moving through magnetic field lines extract energy through a combination of frame dragging and electromagnetic induction. This process may naturally occur around some black holes and could potentially be engineered into a more efficient energy extraction system. It is worth considering the scales involved in the Penrose process. For a stellar mass black hole with 10 times the mass of our Sun, the ergosphere would extend only a few tens of kilometers beyond the event horizon. The precision required to execute the process would be extraordinary, with trajectories calculated to sub-millimeter accuracy. For a supermassive black hole, the scales are larger but still challenging. The ergosphere of the black hole at the center of our galaxy would extend about 20 million kilometers beyond its event horizon, roughly 1/8 the distance from Earth to the Sun. The time dilation effects near a black hole add another layer of complexity. From the perspective of distant observers, processes near the black hole appear to unfold in slow motion. An energy extraction mechanism that operates on a timescale of seconds in its own reference frame might appear to take hours or even days from the perspective of those receiving the energy at a safe distance. These relativistic effects would need to be incorporated into any practical implementation of the Penrose process. The energy gains from a single application of the Penrose process might seem modest, but they could accumulate over time. A civilization could establish multiple energy extraction systems operating simultaneously around a black hole, each sending carefully calibrated streams of matter into the ergosphere and collecting the energized matter that emerges. Over time, a significant fraction of the black hole's rotational energy could be harvested. Critics of the Penrose process as a practical energy source point to several challenges. The precision required is beyond our current technological capabilities by many orders of magnitude. The environment near a black hole is hazardous, with intense radiation, strong gravitational forces that would tear apart conventional materials, and extreme temperatures in any naturally occurring accretion disk. Moreover, the nearest known black holes are many light years from Earth, making the transportation of energy back to our civilization an enormous challenge. Nevertheless, for a sufficiently advanced civilization, these challenges might not be insurmountable. Materials science might produce substances capable of withstanding the extreme conditions near a black hole. Precision navigation and trajectory calculation could be achieved with advanced computers or even artificial intelligences specialized for the task. And the energy transportation problem might be solved through some form of matter-antimatter relay system, or even through exploiting the properties of entangled quantum systems, though the latter remains highly speculative. The total energy available through the Penrose process is vast. A rapidly spinning stellar mass black hole could theoretically yield energy equivalent to the conversion of several solar masses of matter entirely to energy. For a supermassive black hole, the available energy could be millions or billions of times greater. This represents an energy reserve that could power an advanced civilization for timescales far longer than the lifetime of conventional stars. Intriguingly, there is some evidence that nature may already implement versions of the Penrose process. The relativistic jets observed emerging from many accreting black holes may be partially powered by rotational energy extracted through mechanisms similar to what we have described. The magnetic fields threading the ergosphere could naturally create conditions where charged particles follow trajectories that extract spin energy from the black hole, accelerating these particles to the tremendous speeds observed in these jets. As we contemplate the Penrose process, we should acknowledge that it represents just one possible mechanism for extracting energy from a black hole. In the next chapter, we will explore another promising approach, the Blandford-Znajek process, which focuses specifically on how electromagnetic fields can extract rotational energy from black holes. This mechanism may be even more relevant for natural astrophysical systems and potentially for engineered energy extraction as well. The Penrose process exemplifies how the exotic physics near black holes can create opportunities unavailable elsewhere in the universe. By leveraging the peculiar properties of space-time in the ergosphere, it offers a window into how advanced civilizations might someday tap the vast energy reserves of rotating black holes. Though beyond our current technological reach, the theoretical foundation is sound, based firmly on the well-established principles of general relativity. As we drift towards sleep, consider the elegant symmetry of the Penrose process. The most extreme objects in our universe, often viewed as cosmic destroyers, might someday serve as the ultimate power sources. The same warping of space-time that creates the inescapable trap of the event horizon also, through the ergosphere, offers a mechanism for energy extraction unmatched in efficiency. In the dance between matter and the swirling vortex of distorted space-time, we find possibilities that stretch our imagination, but not the laws of physics as we understand them. The Penrose process reveals that even in the darkness surrounding a black hole, there exists the potential for light, for energy, for the sustenance of life and civilization. As you close your eyes, imagine distant beings sending streams of matter into the ergosphere of a black hole in an elegant cosmic dance, extracting the rotational energy of these mysterious objects and using it to power worlds and civilizations far beyond our current reach. This is not merely science fiction, but a possibility grounded in our understanding of the mathematics of curved space-time, a testament to how far our comprehension of the universe has come, and a hint of how far advanced civilizations might someday go in their quest to harness the fundamental forces of nature. Building upon our understanding of the Penrose process, we now turn our attention to another fascinating mechanism for extracting energy from rotating black holes. The Blandford-Znajek process, named after astrophysicists Roger Blandford and Roman Znajek, who first described it in 1977, represents perhaps the most astrophysically relevant energy extraction mechanism and potentially the most promising for advanced technological civilizations. While the Penrose process focuses on the behavior of matter in the ergosphere, the Blandford-Znajek process involves the interaction between electromagnetic fields and the rotating space-time around a black hole. This distinction makes it especially significant because electromagnetic fields can extend far beyond the immediate vicinity of the black hole, potentially allowing for energy extraction from a safer distance. To understand this process, we must first consider what happens when magnetic fields encounter a rotating black hole. In everyday life, we think of space as empty and transparent to magnetic fields. But in the vicinity of a black hole, space-time itself becomes a player in electromagnetic phenomena. The rotation of the black hole drags space-time around it, and this moving space-time affects magnetic field lines in remarkable ways. Imagine a black hole surrounded by a magnetized accretion disk, a common configuration throughout the universe. As conducting plasma spirals through this disk, it generates electric currents, which in turn create magnetic fields. Some of these magnetic field lines will thread through the ergosphere and potentially through the event horizon itself. When this happens, the rotation of space-time twists these magnetic field lines, creating a complex electromagnetic structure around the black hole. This twisting of magnetic fields creates electric potential differences, essentially turning the black hole's rotational energy into electromagnetic energy. The conducting plasma surrounding the black hole provides a medium through which electric currents can flow along these twisted field lines. These currents can accelerate charged particles, creating powerful jets of matter and radiation that escape the black hole system, carrying away some of the black hole's rotational energy. The mathematics describing this process are formidable, requiring sophisticated understanding of both general relativity and electromagnetism. But conceptually, we can think of the rotating black hole and its surrounding magnetic field as a kind of enormous electric generator. Just as a spinning magnet inside a coil of wire generates electric current in the wire, a spinning black hole in a magnetic field generates electric currents in the surrounding plasma. One of the most remarkable aspects of the Blandford-Znajek process is its efficiency. Under ideal conditions, it can extract rotational energy from a black hole with efficiency approaching the theoretical maximum. For rapidly spinning black holes, this could mean converting a significant fraction of the available rotational energy into electromagnetic energy that can escape to the wider universe. The process operates most effectively when the black hole is spinning rapidly and immersed in strong magnetic fields. The power output scales with the square of both the black hole's spin parameter and the strength of the magnetic field. This means that doubling either the spin or the magnetic field strength quadruples the power output. For maximally spinning black holes in strong magnetic fields, the energy output can be enormous, sufficient to power the most energetic phenomena we observe in the universe. Indeed, the Blandford-Znajek process is widely believed to be the primary mechanism powering relativistic jets in active galactic nuclei and quasars. These jets, which can extend for millions of light years, represent some of the most powerful sustained energy outputs in the cosmos. The observation that such jets tend to emerge from regions harboring supermassive black holes provides strong circumstantial evidence for the operation of the Blandford-Znajek process in nature. Let us consider the scales involved. For a typical active galactic nucleus, the central supermassive black hole might have a mass billions of times that of our Sun, with an event horizon spanning billions of kilometers. The magnetic fields threading this region could be thousands or even millions of times stronger than Earth's magnetic field. Under these conditions, the power generated through the Blandford-Znajek process can reach values of 10 to the power of 47 watts or more, millions of times the total luminosity of all the stars in the Milky Way combined. Even for much smaller stellar mass black holes, the process can generate impressive power outputs. A rapidly spinning black hole of 10 solar masses, with magnetic fields similar to those found in some neutron stars, could potentially generate energy at rates comparable to the total output of a medium-sized galaxy. This represents an energy source far beyond anything accessible through conventional means, even nuclear fusion or matter-antimatter annihilation. From the perspective of an advanced civilization seeking to harness this energy, the Blandford-Znajek process offers several advantages over the Penrose process. Perhaps most significantly, it does not require sending physical matter into the dangerous region near the black hole. Instead, the civilization would need to establish and maintain magnetic fields threading the ergosphere and event horizon, potentially from a safer distance. How might such a civilization implement this? One approach would be to construct a magnetized accretion disk around a carefully selected black hole. By controlling the flow of plasma through this disk, the civilization could generate and shape magnetic fields of the desired strength and configuration. Superconducting loops placed at strategic locations around the black hole could help direct and stabilize these fields, ensuring optimal conditions for energy extraction. The generated electromagnetic energy would emerge predominantly along the rotation axis of the black hole, creating powerful jets similar to those observed in active galactic nuclei. To capture this energy, the civilization might construct enormous collector arrays positioned within these jets. designed to convert the kinetic and electromagnetic energy of the accelerated particles into usable forms. Alternatively, if the technological capability exists, the civilization might bypass the natural plasma environment entirely and establish artificial magnetic fields directly. This would require materials capable of maintaining intense magnetic fields in the extreme gravitational environment near a black hole, perhaps leveraging advanced superconductors or exotic states of matter not yet discovered. The challenges of implementing the Blandford-Znajek process for energy harvesting are substantial. The environment near a black hole is harsh, with intense radiation, strong gravitational forces, and extreme temperatures. Maintaining precise control over magnetic field configurations in such conditions would test the limits of even the most advanced technology we can currently imagine. Moreover, the process works most efficiently for rapidly spinning black holes. Finding such black holes, or potentially spinning up more slowly rotating ones, would be an additional challenge. There is evidence that many supermassive black holes in the universe rotate relatively slowly, perhaps due to mergers with other black holes throughout their history, which tend to reduce spin through gravitational wave emission. Nevertheless, for a civilization with sufficient technological capability, these challenges might be surmountable. The reward would be access to an energy source of almost unimaginable magnitude, capable of powering civilizations on scales we can barely comprehend. It is worth noting that the Blandford-Znajek process and the Penrose process are not mutually exclusive. They represent different mechanisms for tapping into the same fundamental energy source, the rotational energy of a black hole. In fact, there are interesting connections between these processes. Both rely on the frame-dragging effect in the ergosphere, and both result in a gradual slowing of the black hole's rotation. A sufficiently advanced civilization might employ both methods simultaneously, or hybrid approaches that combine elements of each. Some astrophysicists have speculated that certain observed features of relativistic jets may indicate the operation of both processes in nature. The inner regions of the jet, closest to the black hole, might be powered primarily by the Blandford-Znajek process, while interactions between the jet and surrounding matter could involve phenomena similar to the Penrose process. Recent computer simulations of black hole magnetospheres have provided additional support for the Blandford-Znajek mechanism. These simulations solve the complex equations of general relativistic magnetohydrodynamics, modeling how plasma behaves in the strong gravitational and electromagnetic fields near a black hole. The results consistently show the formation of jets and the extraction of rotational energy through processes very similar to what Blandford and Znajek described. These simulations also reveal fascinating details about how the process might operate in reality. They suggest that the magnetic field lines threading the ergosphere create regions where electric fields parallel to the magnetic fields can accelerate charged particles to enormous energies. This acceleration mechanism might explain why particles in astrophysical jets can reach speeds tantalizingly close to the speed of light. Another interesting aspect of these simulations is the prediction of what physicists call magnetic reconnection events in the black hole magnetosphere. When magnetic field lines of opposite polarity come close together, they can reconnect in a new configuration, releasing substantial energy in the process. This phenomenon, observed on a smaller scale in solar flares, might contribute significantly to the energy output of black hole systems and could potentially be harnessed by advanced technology. For a civilization considering the use of the Blandford-Znajek process as an energy source, one attractive feature is its sustainability. Unlike many astrophysical energy generation mechanisms, which involve the consumption of matter, the Blandford-Znajek process taps directly into the rotational energy of the black hole itself. This energy reservoir is enormous and very long-lasting. A rapidly spinning supermassive black hole could power a civilization at current Earth levels for timescales far longer than the current age of the universe, even accounting for the gradual spin down of the black hole due to energy extraction. The total extractable energy through this process depends on the black hole's mass and spin. For a maximally spinning black hole, up to approximately 29% of its mass energy can theoretically be extracted as rotational energy. For perspective, a black hole with 10 times the mass of our Sun would have about 2 times 10 to the power of 47 joules of extractable rotational energy. This is roughly equivalent to the total energy our Sun will radiate over its entire 10 billion year lifetime. It is fascinating to consider that nature already implements the Blandford-Znajek process on a grand scale. The enormous jets observed from active galactic nuclei transport energy and momentum across intergalactic distances, influencing the evolution of their host galaxies and even the intergalactic medium. These natural implementations of the process achieve power outputs that dwarf even our most ambitious human energy projects by factors of trillions or more. By studying these natural examples, we gain insights into how an engineered version might function. Observations of how magnetic fields thread the ergosphere, how plasma flows are established and maintained, and how energy is converted and transported provide valuable clues for any future attempt to harness this process technologically. The Blandford-Znajek process also has interesting connections to other areas of physics. The behavior of magnetic fields in curved spacetime provides insights into fundamental questions about the nature of electromagnetism in strong gravitational fields. The acceleration mechanisms in black hole magnetospheres push our understanding of particle physics to its limits, and the global structure of the magnetic field around a rotating black hole connects to deep questions in topology and field theory. For any civilization contemplating the use of black holes as energy sources, the Blandford-Znajek process would likely be among the first mechanisms considered. Its relative safety compared to the Penrose process, its enormous power output, and its sustainability make it an attractive option. The fact that we observe what appear to be natural implementations of the process throughout the universe provides additional confidence in its viability. As we conclude our exploration of the Blandford-Znajek process, we should reflect on what it represents. Here is a mechanism, predicted by our current understanding of physics, that could allow access to energy on scales far beyond anything available through conventional means. It demonstrates that the universe's most extreme objects, often viewed solely as destructive forces, might someday serve as the ultimate power plants for advanced civilizations. In the next chapter, we will turn our attention from the theoretical mechanisms of energy extraction to the practical question of how civilizations might utilize this energy. We will explore concepts such as Dyson spheres adapted for black holes, consider the engineering challenges involved, and speculate on the capabilities that such vast energy resources might enable. As you drift towards sleep, imagine the elegant dance of magnetic field lines around a spinning black hole, twisted by the rotation of space-time itself, channeling the immense rotational energy outward along cosmic jets that illuminate the darkness. Somewhere in our vast universe, perhaps civilizations far more advanced than our own are already implementing versions of the Blandford-Znajek process, tapping into the rotation of the most extreme objects nature has produced to power technologies and achievements beyond our current imagining. When we gaze up at the night sky, contemplating the distant stars and the black holes that lurk beyond our sight, we might wonder if other civilizations exist among those countless points of light. And if they do, might some of them have developed technologies far beyond our own? Technologies that could potentially harness the incomprehensible power of black holes. Imagine a civilization that has survived for millions or perhaps billions of years, one that has exhausted the easily accessible resources of their homeworld and nearby planets. As their energy needs grow, they would need to look toward more exotic power sources. Black holes, with their tremendous energy potential, would be a natural target for such advanced beings. Russian astrophysicist Nikolai Kardashev proposed in 1964 a scale for measuring the technological advancement of civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 can utilize the entire energy output of its host star. And a Type 3, the most advanced, can harness the energy of its entire galaxy. By this classification, humanity hasn't yet reached Type 1 status. But a civilization capable of extracting energy from black holes would likely be approaching Type 2 or Type 3 on the Kardashev scale. Such a civilization might begin by sending robotic probes to scout nearby black holes, particularly those that spin rapidly and have strong magnetic fields, making them ideal candidates for energy extraction. These probes would study the black hole's properties, the surrounding space, and begin the monumental task of constructing the necessary infrastructure. The construction of a black hole energy harvester would be an engineering feat of staggering proportions. One approach might involve creating a vast array of satellites or stations positioned carefully around the black hole, just outside the ergosphere where the Penrose process occurs. These stations would manipulate particles, sending them into precisely calculated trajectories to split and extract energy before being consumed by the black hole. The stations would collect the escaping particles with their boosted energy, converting it to usable power. Another approach might utilize the Blandford-Znayak process, with enormous structures designed to shape and direct the magnetic field lines around the black hole. The energy generated in the magnetic field by the black hole's rotation would be captured by these structures and channeled away as electrical current. But why stop there? A truly advanced civilization might construct something akin to a Dyson sphere around a black hole, a concept sometimes called a Dyson swarm when applied to stars. Named after physicist Freeman Dyson, who proposed in 1960 that advanced civilizations might build structures that completely encompass their star to capture most or all of its energy output. In the case of a black hole, this swarm would not capture light, but would instead be positioned to maximize energy extraction through processes like those described by Penrose and Blandford-Znayak. The materials needed for such megastructures would be immense. An advanced civilization might mine entire planets or asteroid belts to gather the necessary resources. They might utilize self-replicating machines that could build copies of themselves, exponentially increasing their construction capacity until they had enough workers to complete the project in a reasonable time frame. The challenges would be enormous. Operating in the intense gravitational field around a black hole would require materials of incredible strength, perhaps utilizing exotic states of matter or molecular structures we cannot yet conceive. The machines would need to withstand not just gravity, but also intense radiation from the accretion disk and relativistic jets. Communication and coordination across such vast structures would require overcoming significant time dilation effects, where time passes differently depending on proximity to the black hole. And yet, the rewards would be equally enormous. The energy potentially available from a single spinning black hole could power an entire civilization for time spans that dwarf the current age of the universe. A medium-sized black hole, the mass of 10 suns, could theoretically provide up to 10 to the power of 39 watts of power through the Blandford-Znayak process. For comparison, the total power consumption of human civilization is currently around 10 to the power of 13 watts. This means a single black hole could provide 100 trillion times more energy than our entire species currently uses. What might such a civilization do with so much energy? They might create vast habitats, supporting populations of trillions or more. They might engage in engineering projects of galactic scale, moving stars and planets to create more habitable environments. They might power computation on a scale we can barely imagine, simulating entire universes, or uploading the consciousness of their entire species into virtual realms of endless possibility. They might also use this energy for transportation, powering starships that could reach relativistic speeds, allowing them to explore and perhaps colonize their entire galaxy. The energy could power warp drives if such technology ever proves possible, potentially allowing travel that appears to exceed the speed of light from an outside perspective, though without violating the fundamental laws of physics. A civilization's hunger for energy tends to grow exponentially as it advances. Throughout human history, our energy consumption has increased dramatically with each technological revolution. From wood fires to coal to oil to nuclear fission, we have consistently sought more potent energy sources. It seems reasonable to assume that this pattern would continue for any technological civilization, eventually driving them toward the most concentrated energy sources in the universe, black holes. Some scientists have suggested searching for signs of such megastructures as a way to detect advanced alien civilizations. If a civilization were harvesting energy from a black hole, there might be observable effects, such as unusual energy patterns or structures visible with advanced telescopes. This concept falls under the broader field of search for extraterrestrial intelligence, or SETI, which traditionally focuses on detecting radio signals, but increasingly includes searching for technosignatures, physical evidence of advanced technology. The philosopher Olaf Stapledon, writing in the 1930s, imagined future civilizations performing feats of astroengineering far beyond our current capabilities. He described beings who could manipulate stars and harness their energy. Today, theorists extend such visions to black holes, seeing them as the ultimate power sources for civilizations that endure for millions or billions of years. Of course, there are those who question whether any civilization could survive long enough to reach such technological heights. The great silence of the cosmos, the apparent absence of obvious technosignatures, despite the vast number of potential star systems where life could evolve, has led some to propose the concept of a great filter. This filter would be some challenge that prevents most civilizations from reaching an advanced state of technological development. Whether this filter lies in our past, meaning we have already overcome it, or in our future, remains an open question. But if any civilization does survive long enough, and if their understanding of physics continues to advance, they might eventually turn their gaze toward black holes as sources of power. They would need to solve countless engineering problems and develop technologies we can scarcely imagine. They would need to master interstellar travel just to reach suitable black holes. They would need materials science, robotics, and energy management systems far beyond our current capabilities. Perhaps someday, in the far distant future, humanity itself might reach such heights. Or perhaps we might one day detect the technosignatures of other civilizations who have already achieved this milestone, discovering that we are not alone in looking up at the stars and dreaming of harnessing their power. The question of whether civilizations could harness the energy of black holes remains theoretical, constrained by our current understanding of physics and the limitations of our technology. But the laws of physics as we understand them do not forbid it. The universe has gifted us with these cosmic engines of incomprehensible power. It remains for intelligence, whether human or alien, to develop the means to tap into that power. And as we contemplate these possibilities, lying here beneath the blanket of stars, we can appreciate how the same human curiosity that drives us to understand black holes also drives us to imagine how we might one day harness their power. That curiosity, that drive to understand and utilize the forces of nature, may be the most powerful force we possess. It has taken us from caves to cities to the beginnings of space exploration. Perhaps, given enough time, it will take us further still, to the very edges of black holes, where we might reach out and draw power from the darkness. Long before scientists seriously contemplated harnessing the energy of black holes, writers of science fiction had already begun exploring this fascinating possibility. Science fiction has always served as a playground for scientific ideas, a place where theories and concepts can be extended beyond their current boundaries and into the realm of what might someday be possible. Black holes, with their mysterious and powerful nature, have proven to be particularly fertile ground for such imaginative explorations. The relationship between science fiction and science fact is often cyclical, with each influencing the other. Many scientists cite science fiction as an early inspiration that led them to their careers, while science fiction writers frequently draw upon the latest scientific discoveries to fuel their creative works. This dance between imagination and investigation has helped shape our cultural understanding of phenomena like black holes. One of the earliest notable appearances of something resembling a black hole in science fiction came in the 1937 short story The Star Stealers by Edmund Hamilton. The story featured what Hamilton called a dark star, with gravity so intense that nothing, not even light, could escape it. This was written before the term black hole was coined by John Wheeler in 1967, yet it captured many of the essential features that we now associate with these cosmic phenomena. As scientific understanding of black holes developed throughout the 20th century, science fiction evolved alongside it. By the 1970s and 80s, black holes had become common elements in science fiction stories, often serving as power sources for advanced civilizations or as gateways to other dimensions or universes. Larry Niven's 1974 novel, The Hole Man, featured a microscopic black hole used as a power source, presaging later scientific discussions about the potential use of micro-black holes for energy generation. Though creating such tiny black holes remains far beyond our current technological capabilities, the concept demonstrated how science fiction can explore the implications of theoretical physics in practical applications. Perhaps one of the most famous depictions of black hole energy utilization in science fiction appears in the Star Trek universe. The Romulan Empire's starships are powered by artificial quantum singularities, essentially controlled black holes that serve as inexhaustible energy sources. The writers of Star Trek imagined that such technology would be possible for a civilization thousands of years more advanced than our own, reflecting the immense engineering challenges that would be involved. In the 2014 film Interstellar, directed by Christopher Nolan, with scientific consultation from physicist Kip Thorne, a supermassive black hole named Gargantua plays a central role. While the film doesn't directly depict energy harvesting from the black hole, it does showcase other theoretical aspects of black hole physics, such as gravitational time dilation and the visual appearance of an accretion disk. The scientific accuracy of many elements in the film helped bring current theoretical understanding of black holes to a wider audience. The 1999 anime series, Outlaw Star, featured ships powered by mana generators that drew energy from small artificial black holes. This concept combined the scientific idea of black hole energy extraction with more mystical elements, demonstrating how science fiction often blends scientific concepts with fantastic ones to create compelling narratives. In Alastair Reynolds' Revelation Space series, an advanced alien civilization known as the Amarantin constructed a massive structure around a neutron star to harness its energy before they were wiped out by a mysterious force. While not specifically a black hole, this depiction of stellar energy harvesting represents the kind of megastructure engineering that might be required for black hole energy extraction as well. Charles Stross's novel Iron Sunrise features a civilization that has weaponized stars by causing them to explode into supernova, which can then form black holes. This darker take on stellar engineering explores not just the potential benefits, but also the dangers of manipulating such powerful cosmic forces. One particularly interesting depiction appears in the 2012 novel The Hydrogen Sonata by Iain M. Banks, part of his Culture series. It describes an ancient civilization that has moved its entire population into computational substrates powered by the energy extracted from millions of artificial black holes. This portrayal aligns with speculation among some futurists that sufficiently advanced civilizations might eventually abandon biological existence in favor of more durable computational forms, which would require vast amounts of energy to sustain. Science fiction has also explored the use of black holes not just as energy sources, but as propulsion systems. In Stephen Baxter's Zeelee sequence, spaceships maneuver by manipulating microscopic black holes. In Peter F. Hamilton's Night's Dawn trilogy, starships create temporary microscopic black holes ahead of them to warp space and achieve faster than light travel. While such applications remain firmly in the realm of fiction, with our current understanding of physics, they demonstrate the creative ways in which writers have imagined harnessing the immense gravitational power of these cosmic phenomena. Beyond the practical applications of black hole energy, science fiction has also explored the philosophical implications of wielding such tremendous power. In Greg Egan's Diaspora, posthuman civilizations have mastered the ability to create and manipulate black holes, giving them godlike power over matter and energy. The story explores how such mastery might change the very nature of consciousness and existence. The ability to harness black hole energy often serves as a marker in science fiction for what we might call a post-scarcity civilization, one that has solved the fundamental problem of limited resources that constrains human society today. With access to the virtually limitless energy of black holes, such civilizations are free to expand, create, and explore in ways that would be impossible under the energy constraints we currently face. This theme appears in numerous works, including Vernor Vinge's A Fire Upon the Deep and Cixin Liu's The Three-Body Problem trilogy, where advanced civilizations are distinguished from less developed ones primarily by their ability to harness increasingly powerful energy sources, culminating in the energy of stars and black holes. Science fiction also frequently explores the dangers and unintended consequences of such powerful technology. In the movie The Black Hole, released in 1979, a scientist's obsession with harnessing the power of a black hole leads to disaster. In the 2017 video game Prey, experiments with harnessing energy from the space around black holes inadvertently open a connection to hostile alien entities. These cautionary tales remind us that with great power comes great responsibility, and that technologies capable of harnessing such immense forces could pose existential risks if misused or poorly understood. Another fascinating concept explored in science fiction is the idea of creating artificial black holes for energy generation. In the 2011 film Source Code, a device creates what is essentially a localized black hole effect to power a virtual reality simulation. While the physics depicted is highly speculative, the concept of artificially generated micro-black holes has been discussed in theoretical physics, though creating them would require energies far beyond our current capabilities. The visual depiction of black holes in science fiction has evolved significantly over time, influenced by advances in our scientific understanding. Early representations often showed black holes simply as dark spheres against the backdrop of space. As understanding of gravitational lensing and accretion disks developed, more sophisticated and accurate depictions began to appear, culminating in the 2080s scientifically rigorous visualization created for Interstellar, which was based on actual computer simulations using the equations of general relativity. The influence of science fiction on public perception of black holes cannot be overstated. For most people, their first encounter with the concept of a black hole comes not through scientific literature, but through science fiction in books, movies, or television shows. These fictional portrayals shape how we imagine these invisible cosmic entities and often spark interest in the actual science behind them. Many astrophysicists, including Stephen Hawking and Neil deGrasse Tyson, have acknowledged the role that science fiction played in inspiring their interest in cosmic phenomena like black holes. This illustrates the powerful role that science fiction can play in popularizing complex scientific concepts and inspiring the next generation of researchers. As our scientific understanding of black holes continues to advance, science fiction will undoubtedly evolve alongside it, finding new and creative ways to imagine how future civilizations might harness these cosmic powerhouses. Perhaps someday, what we now consider science fiction will become science fact, as humanity or other intelligent beings develop the technology to tap into the enormous energy potential that black holes represent. In this way, science fiction serves not just as entertainment, but as a form of thought experiment, allowing us to explore the implications and possibilities of scientific theories in ways that pure scientific discourse often cannot. By imagining what might be possible with technologies far beyond our current capabilities, science fiction helps us to dream bigger and think more creatively about the ultimate limits of technological advancement. And as we drift here, contemplating these fantastic possibilities, we can appreciate how the human imagination soars beyond the boundaries of what is currently possible, reaching toward what might someday be achieved. In the dark of night, as stars twinkle above, perhaps we are not just looking at distant suns, but at the future power sources of a humanity that has spread across the galaxy, drawing energy from the most powerful objects in the universe. Current research into black holes continues to unveil their mysterious nature and incredible power. Every observation we make brings us closer to understanding how these cosmic giants might someday become the ultimate power plants of advanced civilizations. Our telescopes and instruments are gradually revealing the secrets behind the immense energy processes occurring around black holes throughout the universe. Scientists around the world are working tirelessly to understand the complex physics of black holes. The Event Horizon Telescope collaboration made history in 2019 when they captured the first ever image of a black hole shadow. This groundbreaking achievement showed us the silhouette of the supermassive black hole at the center of galaxy Messier 87, a massive elliptical galaxy located about 53 million light-years from Earth. This black hole contains a mass equivalent to 6.5 billion suns. What made this observation so significant was not just the visual confirmation of black holes, but the detailed information it provided about the surrounding environment. The bright accretion disk that appears to encircle the dark shadow reveals intense energy processes occurring just outside the event horizon. Scientists can study this radiation to better understand how energy moves and transforms in these extreme environments. More recent observations using X-ray telescopes have focused on measuring the spin rates of black holes. Spin is particularly important because it directly relates to energy extraction possibilities. The faster a black hole spins, the larger its ergosphere becomes, creating more opportunities for processes like the Penrose mechanism to operate efficiently. Astronomers have discovered several black holes spinning at rates approaching the theoretical maximum, with some rotating at more than 90% of the maximum possible speed allowed by physics. One particularly interesting object of study is the black hole in galaxy NG C4258. Observations indicate that this black hole may be spinning at nearly the maximum rate possible. Such rapidly spinning black holes create space-time conditions most favorable for energy extraction through both the Penrose and Blandford-Znajek processes. Research teams are also investigating the relationship between black hole properties and their relativistic jets. These powerful beams of particles and radiation that shoot out from near the poles of many black holes represent natural energy extraction in action. By studying how these jets form and accelerate to nearly the speed of light, scientists hope to gain insights that could inform future artificial energy harvesting techniques. The LIGO and Virgo gravitational wave detectors represent another revolutionary avenue of black hole research. Since the first detection of gravitational waves in 2015, scientists have observed dozens of black hole mergers throughout the universe. These cataclysmic events release enormous amounts of energy in the form of gravitational waves, with some merger events briefly outshining the combined light output of all stars in the observable universe, despite releasing this energy in a form we cannot see with traditional telescopes. Theoretical physicists are developing increasingly sophisticated computer simulations of black hole environments. These simulations model the behavior of matter and energy in the extreme gravitational fields near black holes, allowing scientists to predict how various energy extraction methods might perform. Some simulations suggest that under the right conditions, the efficiency of energy extraction from a rapidly spinning black hole could approach 20 to 30%, far exceeding the efficiency of nuclear fusion at approximately 1%. Laboratory experiments on Earth are also contributing to our understanding of black hole physics. While we cannot create actual black holes in laboratories, researchers can study analog systems that mimic certain properties of black hole spacetime. For example, scientists have created acoustic black holes in superfluids, where sound waves cannot escape beyond a certain boundary, similar to how light cannot escape a black hole. These analog systems allow for testing predictions about phenomena like Hawking radiation in controlled environments. Looking toward the future, several next-generation telescopes promise to reveal even more about black holes. The James Webb Space Telescope, launched in 2021, has provided unprecedented infrared observations of distant galaxies, allowing scientists to study the relationships between supermassive black holes and their host galaxies in the early universe. This information helps us understand how black holes grow and evolve over cosmic time. The planned next-generation Event Horizon Telescope Array will improve upon its predecessor with additional radio telescopes and more sensitive instruments. This enhanced network will provide sharper images of black hole shadows and the surrounding accretion disks, potentially revealing dynamic processes occurring near the event horizon in real time. These observations could directly test predictions about energy flows in black hole systems. In space-based X-ray astronomy, future missions like the Advanced Telescope for High-Energy Astrophysics, or ATHENA, will study the hot, energetic environments around black holes with unprecedented detail. By precisely measuring the spectra of X-rays emitted from material just before it crosses the event horizon, scientists can map the structure of space-time itself in these regions and better understand the energy conversion processes taking place. Quantum gravity researchers are also making strides in understanding what happens at the very center of black holes, where our current theories break down. While still highly theoretical, advances in quantum gravity could eventually reveal new mechanisms for energy extraction that go beyond classical approaches like the Penrose process. Some theoretical physicists propose that information conservation principles might allow for energy to be extracted from the quantum properties of black holes themselves, not just from their classical gravitational fields. Experimental evidence for Hawking radiation, the theoretical quantum effect where black holes slowly emit particles and lose mass, remains elusive. However, if confirmed, this process would represent a direct conversion of black hole mass into energy through quantum mechanisms. While natural Hawking radiation is far too weak to serve as a practical energy source, an advanced civilization might find ways to enhance or catalyze this process. The search for microscopic black holes produced in particle accelerators continues as well. While the Large Hadron Collider has not yet detected any such objects, certain theoretical models predict their possible creation in high-energy collisions. If produced and stabilized, microscopic black holes would provide laboratory settings for testing energy extraction techniques on manageable scales before attempting them with astrophysical black holes. Scientists are also exploring theoretical connections between black hole thermodynamics and information theory. The holographic principle, which suggests that all the information contained within a volume of space can be represented on its boundary surface, has profound implications for understanding black hole entropy. This principle forms the foundation of the anti-de Sitter space conformal field theory correspondence, or ADS-CFT correspondence, a theoretical framework that connects gravity theories with quantum field theories, and could eventually lead to new insights about energy and information extraction from black holes. Private companies are beginning to take interest in the long-term potential of black hole energy extraction. While still firmly in the realm of speculative research, some forward-thinking corporations are funding theoretical studies on black hole power generation. These companies understand that even if practical applications lie centuries away, the fundamental research could yield unexpected technological benefits in the nearer term. Scientific progress in this area faces significant challenges. The environments near black holes cannot be directly replicated in laboratories, and our observations are limited by vast cosmic distances. Additionally, the most promising black hole energy extraction methods require technology far beyond our current capabilities. However, the history of science shows that theoretical understanding often precedes practical application by centuries. The basic principles of electromagnetic induction were established long before they enabled the construction of modern power plants. Perhaps the most important current research involves the search for naturally occurring evidence of energy extraction around black holes. Some astrophysicists have proposed that certain unexplained phenomena in the universe might be evidence of artificial structures built by advanced civilizations to harness black hole energy. While highly speculative, the search for such technosignatures represents a bridge between pure scientific research and the practical applications that might someday follow. As we continue to develop more powerful observational tools and more sophisticated theoretical models, our understanding of black holes grows steadily more complete. Each discovery brings us incrementally closer to the day when humanity might possess the knowledge necessary to tap into these cosmic wellsprings of energy. The journey from theoretical understanding to practical application is likely to be measured in centuries rather than decades, but the foundation for that journey is being laid by scientists working today. The most exciting aspect of current black hole research is how it continually surprises us. Black holes were once thought to be purely destructive cosmic entities, but we now recognize them as dynamic systems that play vital roles in galactic evolution. They generate powerful jets, create heavy elements through associated processes, and shape the formation of stars and planets throughout their host galaxies. As we discover more about these functions, we may identify additional mechanisms for potential energy extraction that nobody has yet conceived. One of the most profound insights from black hole research comes from considering the ultimate fate of these objects. Through the incredibly slow process of Hawking radiation, black holes are theoretically expected to eventually evaporate completely. For a black hole with the mass of our Sun, this process would take approximately 10 to the power of 67 years, an almost incomprehensibly long time. During the final moments of evaporation, the power output would briefly surge to enormous levels. While no naturally occurring black holes in our universe have had time to reach this stage yet, an advanced civilization with sufficient patience and foresight might someday harness this terminal burst of energy. When we contemplate the vast energy reserves locked within black holes, we cannot help but consider the philosophical implications of such power. What would it mean for a civilization to harness the most extreme objects in the universe? How would such abilities transform their relationship with the cosmos? These questions invite us to reflect not just on the physics of black holes, but on our own place in the universe and the ultimate destiny of intelligent life. The pursuit of black hole energy represents more than just a technological challenge. It embodies humanity's deepest desires to understand and harness the fundamental forces of the universe. While practical applications may lie far in our future, the journey of exploration has already begun through our telescopes, our equations, and our imaginations. Each discovery about black holes brings us one step closer to a future where the most destructive forces in the universe might be tamed to serve as the ultimate power source for an advanced civilization spanning the stars. Throughout history, human societies have been defined by the energy sources they could harness. From wood fires that warmed ancient caves to the nuclear reactors powering modern cities, each advance in energy technology has transformed our relationship with the natural world. The potential harnessing of black holes represents the ultimate extension of this journey, raising profound questions about power, ethics, and our cosmic destiny. When we contemplate extracting energy from black holes, we are essentially discussing the most extreme form of power generation conceivable within the laws of physics. The energy contained within a single moderate-sized black hole exceeds all the energy our civilization has ever produced or consumed. With such vast power comes equally vast philosophical questions. What responsibilities would accompany the ability to tap into such cosmic forces? How would a civilization capable of harnessing black holes approach its relationship with the universe? The philosopher Hans Jonas proposed the principle of responsibility, arguing that advanced technological capabilities create corresponding ethical obligations. A civilization with access to black hole energy would possess power approaching that of the natural cosmic processes that shape galaxies. Such capabilities would demand an unprecedented level of ethical maturity and foresight. Decisions about how to use such energy would affect not just individual planets, but potentially entire star systems or galaxies. This connects to the broader philosophical concept of cosmic stewardship. If intelligent life is rare in the universe, then perhaps technologically advanced civilizations have an implicit responsibility to preserve cosmic potential. Energy extracted from black holes could be used to prevent natural catastrophes, extend the habitable lifetime of star systems, or even create new conditions suitable for life. Rather than merely consuming resources, a truly advanced civilization might take an active role in nurturing the universe's capacity for complexity and consciousness. The Russian physicist Nikolai Kardashev proposed a scale for measuring technological civilizations based on their energy consumption. A Type 1 civilization harnesses the energy resources of an entire planet. A Type 2 controls the energy of a star. A Type 3 commands the energy of an entire galaxy. Black hole energy extraction would represent a step beyond Type 2, potentially putting a civilization on the path toward the third level. Each transition on the Kardashev scale would likely coincide with profound transformations in social organization, values, and objectives. Consider how our relationship with nature has evolved alongside our energy technologies. Early humans saw themselves as simply part of the natural world. The Industrial Revolution positioned humanity in opposition to nature, extracting resources and transforming environments. More recently, some societies have attempted to develop sustainable relationships with natural systems. A black hole harnessing civilization would need to evolve this relationship further, understanding itself as a conscious participant in cosmic processes spanning billions of years. The philosopher and futurist Olaf Stapledon explored such themes in his novel Star Maker, imagining civilizations that evolve to encompass entire galaxies and ultimately to engage with the consciousness of the universe itself. While purely speculative, such visions highlight how technological advancement necessarily transforms a civilization's self-understanding and purpose. The engineers who first controlled fire could never have imagined nuclear power, just as we struggle to truly comprehend what it would mean to harness a black hole. There's a beautiful irony in the concept of extracting energy from black holes. These objects were once considered the ultimate symbols of destruction, regions where matter and energy disappeared forever from our universe. Yet modern physics suggests they might become the ultimate power sources, cosmic engines driving unimaginable technological achievements. This transformation from destroyer to creator reflects a deeper pattern in human understanding, where increased knowledge reveals unexpected potential in what was once feared. Russian cosmist Nikolai Fedorov proposed that advanced civilizations would eventually take responsibility for resurrecting all beings who had ever lived. While this specific vision seems implausible, it represents a broader philosophical tradition suggesting that truly advanced technology blurs the line between creation and resurrection. The vast energy available from black holes could theoretically power computational systems capable of simulating entire universes, preserving or recreating patterns that would otherwise be lost to entropy. The philosopher John Leslie explored the concept of axiarchism, the idea that the universe exists because goodness requires existence. In this framework, the evolution of consciousness and intelligence represents the universe coming to know itself. If such a perspective holds any truth, then the ability to harness black holes might serve a deeper cosmic purpose, allowing the universe to consciously shape its own evolution rather than merely succumbing to blind thermodynamic processes. Many philosophical traditions address the tension between power and wisdom. From the Tao Te Ching's warnings about the dangers of overreaching to Plato's concept of philosopher kings, human thinkers have recognized that power without corresponding wisdom leads to destruction. Black hole energy would represent a level of power almost beyond comprehension. Would the wisdom required to manage such power evolve naturally alongside the technical capabilities? Or would civilizations face dangerous imbalances between what they could do and what they should do? We might find insight in Buddhist concepts of interconnectedness. A civilization capable of manipulating black holes would need to deeply understand its place within cosmic systems and the consequences of its actions across vast timescales. The Buddhist principle of ahimsa, or non-harm, would need to be expanded to encompass potential effects spanning billions of years and countless potential life forms. Every decision to harness or redirect cosmic energy would carry implications for the future evolution of matter and potentially consciousness throughout affected regions. Some philosophers have proposed the concept of cosmic humility as a necessary virtue for advanced technological civilizations. This approach recognizes that despite enormous technological capabilities, the universe will always contain mysteries and forces beyond complete control or understanding. Even while harnessing the power of black holes, a wise civilization would maintain awareness of its limitations and the inherent uncertainty in complex natural systems. This tension between tremendous power and fundamental uncertainty would shape their entire approach to existence. There's a profound question of meaning embedded in the pursuit of such cosmic engineering projects. Why would a civilization undertake the enormous effort required to harness a black hole? Pure survival might motivate initial efforts, but beyond that, what purposes would justify such undertakings? The philosopher Bernard Williams explored the concept of categorical desires, those aims that give meaning to existence itself rather than serving instrumental goals. Perhaps the ultimate categorical desire would be to ensure the flourishing of consciousness against the universe's tendency toward disorder. The field of environmental ethics offers relevant perspectives. Traditional environmental ethics focuses on humanity's relationship with Earth's natural systems, but similar principles could apply at cosmic scales. Just as we now recognize the value of preserving Earth's biodiversity, a cosmic environmental ethic might recognize the value in preserving the universe's diversity of phenomena, from the birth of stars to the dynamic dance of galaxies. Energy harvested from black holes could serve preservation efforts rather than merely fueling consumption. Temporal ethics also becomes important when considering black hole energy. The philosopher Derek Parfit examined how we should weigh the interests of future generations against present needs. With black hole energy systems potentially operating over millions or billions of years, the temporal scope of ethical consideration would need to expand dramatically. Decisions made at the beginning of such projects would affect countless future generations, raising questions about intergenerational justice and responsibility that dwarf our current ethical frameworks. The conquest of black hole energy would represent humanity's ultimate triumph over entropy, the universal tendency toward disorder that drives the arrow of time. Yet even this mastery would be temporary. Current physics suggests that the universe itself has a finite lifespan, with even black holes eventually evaporating through Hawking radiation. This tension between tremendous but still limited power creates a unique existential situation. Even at the height of technological development, civilizations would face the knowledge of ultimate cosmic mortality. This brings us to philosophical questions about the purpose of technological advancement. Is the goal simply to survive as long as possible against the forces of cosmic decay? Or is there something more meaningful to be achieved through consciousness and intelligence? The philosopher Karl Jaspers spoke of boundary situations, moments where humans confront the fundamental limitations of existence. Black hole harnessing civilizations would live constantly at such boundaries, their enormous power always contextualized by even greater cosmic forces. Some philosophers have proposed that truly advanced civilizations might transcend traditional notions of progress altogether. Rather than constantly expanding and consuming more energy, they might find equilibrium states that allow for the continued flourishing of consciousness without requiring ever-increasing resource utilization. In this view, black hole energy might serve not endless growth, but rather deep sustainability, powering civilizations designed to maintain themselves through cosmic timescales without continuous expansion. The very concept of civilization would likely transform alongside these technological capabilities. Our current understanding of society is tied to specific planetary contexts and limited resources. A civilization spanning multiple star systems and powered by black holes would develop entirely new social structures, values, and organizing principles. Perhaps individual planets or star systems would become like the cities of today, each with unique cultures but connected through interstellar networks of trade, communication, and shared purpose. One of the most profound philosophical implications relates to the possibility of creating new life and new universes. Theoretical physics suggests that with sufficient energy and control over space-time, advanced civilizations might create artificial universes through controlled singularities. Black hole energy could power such godlike creative acts. This raises ultimate questions about the nature and purpose of existence. Would such creations have moral status? What responsibilities would creator civilizations bear toward the potentially conscious beings evolving within their manufactured cosmos? Russian philosopher Nikolai Berdyaev distinguished between technical and spiritual progress, arguing that the former without the latter leads to dehumanization. A civilization with black hole technology would face this dilemma at cosmic scales. Would their mastery of fundamental physical forces be matched by corresponding wisdom in how to direct such capabilities? The history of human technological development shows periods where technical abilities outpaced ethical frameworks, leading to destruction and suffering. Similar imbalances at cosmic scales could have consequences beyond imagination. Yet there's also tremendous hope in these philosophical reflections. If consciousness can evolve to the point of harnessing black holes responsibly, perhaps the universe itself contains an inherent tendency toward greater awareness and purpose. The philosopher Pierre Teilhard de Chardin proposed the concept of the omega point, a state of maximum complexity and consciousness toward which evolution naturally tends. Black hole energy might serve as the final technological key, unlocking this ultimate state of cosmic self-awareness. There's a beautiful symmetry in the idea that the most destructive objects in the universe could ultimately power the greatest creative achievements of conscious beings. This transformation embodies a deep philosophical principle that opposites contain and create each other. Darkness enables light, destruction enables creation, and perhaps the ultimate gravitational wells of the cosmos enable the ultimate flowering of intelligence and purpose. As we gaze up at the night sky, knowing that invisible black holes lurk among the stars, we touch the boundary between present limitation and future potential. Our current civilization remains confined to a single fragile planet, yet our minds can already conceive of harnessing the most powerful objects in the universe. This capacity for imagination itself represents a kind of power, the ability to envision possibilities that might someday become reality through the patient accumulation of knowledge and wisdom across generations. The story of black hole energy ultimately reflects our own search for meaning in a vast and ancient universe. As ephemeral beings living brief lives, we seek connection to something larger and more enduring than ourselves. The stars and black holes will outlast us by billions of years, yet through understanding and potentially harnessing these cosmic objects, we forge a relationship with eternity. Whether or not human descendants ever tap into black hole energy, the very possibility enriches our present moment with cosmic significance. We come now to the end of our journey through one of the most fascinating frontiers where theoretical physics meets speculative technology. The idea of harvesting energy from black holes represents the ultimate dream of cosmic engineering, a possibility that pushes against the very boundaries of what physics allows. As we drift towards sleep beneath the canopy of stars, let us carry with us the wonder of these cosmic possibilities. Throughout human history, we have looked to the night sky with awe and curiosity. Our ancestors saw patterns in the stars and created myths to explain the heavens. Today, our scientific understanding reveals a universe even more magnificent than ancient imaginations could conceive. Black holes stand as perhaps the most mysterious and powerful objects in this cosmic landscape. Once thought to be purely destructive forces, regions where matter and light disappear forever, we now understand them as dynamic systems that shape galaxies and potentially offer untapped reserves of energy beyond anything our civilization has yet harnessed. The mathematics describing these objects has revealed unexpected possibilities. Spinning black holes create regions of space-time where energy can theoretically be extracted rather than merely consumed. The ergosphere becomes a cosmic wellspring. a place where the universe offers up energy to those with sufficient knowledge and technology to claim it. While practical black hole energy harvesting remains far beyond our current capabilities, perhaps thousands or millions of years in our future, the theoretical foundation has already been established. The Penrose process and the Blandford-Znajek mechanism provide conceptual blueprints for how advanced civilizations might someday tap into these cosmic powerhouses. Imagine for a moment civilizations spanning multiple star systems, their energy needs supplied not by burning fossil fuels or even by harnessing the power of stars, but by the rotational energy of supermassive black holes at galactic centers. Such civilizations would operate on timescales and energy budgets almost beyond comprehension, their technological achievements appearing as magic to our current understanding. The cosmic perspective offers a particular kind of comfort. As you rest, consider that throughout the universe, countless black holes are spinning in the darkness, each one containing enough energy to power civilizations for trillions of years. This energy exists whether we harness it or not, a patient potential waiting through the slow turn of cosmic ages. Perhaps the story of intelligent life throughout the universe follows a common pattern. Beginning on planets circling ordinary stars, life eventually develops technology and understanding sufficient to reach beyond its birthplace. As energy needs grow, civilizations look first to their sun, then to other stars, and finally to the black holes that offer the richest energy resources of all. If other intelligent species exist among the hundreds of billions of galaxies in our observable universe, some may have already achieved what remains theoretical for us. Perhaps at this very moment, while we sleep, ancient civilizations are drawing power from the spinning hearts of galaxies, their existence sustained by the very objects once thought to be purely destructive. There is a beautiful symmetry in this possibility. Black holes form from the catastrophic collapse of massive stars, events that seem to represent endings. Yet through the processes we've explored, these cosmic endings become new beginnings, sources of energy that could sustain life and consciousness far beyond the lifespans of ordinary stars. As your consciousness drifts towards sleep, imagine humanity's distant descendants, inheritors of scientific knowledge accumulated over thousands of generations, constructing their first black hole harvester. Perhaps they send robotic systems to orbit close to stellar black holes, carefully positioning electromagnetic fields to extract energy through the Blandford-Znajek process. Or maybe they perfect the art of directing carefully prepared masses into the ergosphere, capturing the excess energy released through the Penrose process. With such power at their disposal, what marvels might they create? Perhaps they would ensure the survival of consciousness against all threats, preserving the accumulated wisdom and beauty created by intelligent beings. They might engineer habitable environments to last billions of years, long after the last natural stars have burned out. The philosophical implications of such mastery over cosmic forces are profound. A civilization capable of harnessing black holes would stand at a unique threshold, their technological capabilities approaching the fundamental limits imposed by physics itself. They would face questions of purpose and meaning that we can barely formulate, let alone answer. Yet even such godlike technology would face ultimate limitations. The laws of thermodynamics still apply at cosmic scales. Even black holes eventually dissolve through Hawking radiation, returning their mass energy to the universe over unimaginably long timescales. The universe itself appears to have a finite lifespan, with even black hole-powered civilizations facing an eventual cosmic night. These ultimate horizons need not diminish the wonder of what might be achieved. Perhaps the true miracle lies not in achieving immortality, but in the journey of understanding itself. From our first curious glances at the night sky to mathematical models revealing the secrets of black holes, human consciousness has shown a remarkable capacity to comprehend the cosmos that birthed it. The universe has organized a small portion of itself into beings capable of understanding black holes, beings who can now envision tapping into their enormous energy reserves. This alone stands as a profound achievement, regardless of whether such visions ever become reality. As you fall deeper into sleep, carried by these cosmic thoughts, remember that you are connected to this grand cosmic story. The atoms in your body were forged in ancient stars. The laws of physics that govern black holes also govern the beating of your heart and the firing of neurons in your brain. The same universe that creates supermassive black holes has also, through its long evolutionary history, created minds capable of understanding them. In the darkness behind your closed eyelids lies a mirror of the cosmic darkness between stars, a reminder that rest and activity, creation and destruction, exist in eternal balance throughout the universe. Black holes, perhaps the most extreme objects in existence, embody this duality perfectly, objects of both ultimate destruction and potential creation. Sleep now, with the gentle knowledge that throughout our galaxy, black holes spin in patient silence, their enormous energy reserves waiting like cosmic savings accounts for civilizations wise enough to access them without destruction. Whether human descendants ever harness this power or not, the possibility itself enriches our understanding of the universe and our potential place within it. In the depths of darkness, there lies a wellspring of power, waiting for minds bold enough to reach in. Sleep now, beside the giants who spin in silence, carried by the energy of the universe that surrounds us all, connecting past to future across the vast expanse of cosmic time.